My name is Kala. I'm here to talk to you about Bayesian classification. It's kind of a dense subject, and I'll try my best to describe it in a way that is very palatable. So, Bayesian classification is essentially a machine learning model that uses a probabilistic approach to classify data. So, if you're looking at your machine learning tree, there's two different sections. There is supervised learning and there's unsupervised learning. Supervised learning has human intervention happen. This human intervention basically means that the humans are telling the computer what to learn, and in the unsupervised learning, there is no human intervention, so the computer does the learning by itself. So in this model, it is a supervised learning technique to classify data. And it has a lot of cool things about it that makes it good for certain scenarios and not so good for other scenarios, right? But there will be a few things you need to understand before we go into the high-level application and concepts of Bayesian classifiers. These things include Bayes' theorem, Bayesian belief networks, directed acyclic graphs, and conditional probability tables. So this is Bayes' theorem. Bayes' theorem is an important thing because it allows us to flip a probability around and get a different dependencies on like x given something, right? So I know this looks scary now, but we're going to go through every piece of this theorem and kind of dissect what it means. So let's proceed. Understanding Bayes' theorem. All of these things have a name, right? So let's go through each one individually. Priors are just how probable is the hypothesis before we observe anything at all. A coin flip is a good example because of the fact that when you look at a coin flip, it's a 50-50% chance no matter what. So if I had to ask you what your prior belief was in the hypothesis that it was going to be a tails, you could answer to me 50%, and that would be a reasonable amount, right? So priors are something that we humans can control. It's kind of like a hyperparameter for the naive Bayes theorem. So we can tune it together to things we know. The problem arises where if we don't know what good priors are for our problem is, then we might not have a very awesome model to begin with, but things converge over time, typically. So even if we have really bad priors, over time they will get fixed. But you really want to choose close things to what should happen. Likelihood is how probable is the evidence given our hypothesis. Often we can calculate this from our data set. Therefore, we can easily calculate this. Now, it doesn't necessarily seem very easy to calculate at this moment, but when we get this, what we really want to do is flip it. We want to get the posterior, which is kind of like the opposite of the likelihood. We have the marginal, which is how probable is the evidence. So the evidence being whatever feature you're looking at. So if the feature is like heads or tails, it would be also 0.5. Posterior is what we're looking for. This is the flip I was talking about. It's how probable is the hypothesis given the evidence, which makes sense intuitively. It's like, how probable is that thing being a cat given that it's fluffy and has whiskers and things of that nature, right? So how does this help us understand what we're doing, right? So let's move into some sort of an example of some sort, and I'm going to use an example of clowns, right? Now, before we go into this example, I'm going to do like a thought experiment with you. So if we were on a playground, right, and we're playing in a sand pit, and we're making sandcastles, what I'm listening to you right now is the features of where we're at and what we're doing. These things are reasonable things to be around us, right? So if I look on the ground and see something like yellow and it's small, there's a high chance it's probably a shovel to, scoop the sand. This is a reasonable assumption, and it would, if it was like a semi-truck somehow sitting there in the sand, that would be kind of hard to believe, right? It's kind of the same concept with the naive Bayes, or just the Bayes theorem in general. It's essentially saying if something's very likely to happen, it probably is that thing. So that's kind of what we're getting at here. So in this example 1 about clowns, right? I just pulled a bunch of numbers out of my mind, and we're going to do some quick math here. So if the probability of A, which A is a clown, is 0.05, right? And B is the probability of large feet, which is 0.12. So these are fractional amounts. The reason they're fractional amounts is probability is always between 0 and 1. So really, the P of A of 0.05 is 5%. The P of B is 12%. And if we say we know that 85% of clowns have big feet, we could say, what is the chance of someone being a clown given they have big feet? Which corresponds to, if you look at our equation, P of A given B. That pipe bar means given. So if you say equals, we just plug and chug. So what is the probability of the evidence given the hypothesis? And that would be the 85%, right? The probability of the hypothesis itself, which is the probability of someone being a clown, is 0.05. And then divided by the probability of the evidence, which is the probability of having big feet, which is the 12%. And if we plug and chug, we get about a 35% chance of someone being a clown, which makes a lot of sense. Pretty creepy, Let's move on. Where did I get these numbers, though? It makes no sense. I just kind of pulled them out of my head. Well, yes, these things can actually be calculated by data sets, which is what we're trying to do most of the time with machine learning. We have some data set S, and we're trying to use data set S and run it on machine learning algorithms to give us good, reliable classification. And like I said, naive Bayes is one of the ways to get some good classification depending on what S contains, or the data set contains. So to bring this into more light, we need to talk about conditional probability tables, right? Like, how do we get this information from a data set? Well, it's quite simple. It's all about counting. So I'm going to imagine we had a data set and we counted these things up out of the data set. So we have columns and we have, who survived and died in these columns, inside the rows. I'm sorry. The rows are survived or died, and the columns are what class the passenger was in. And we have a question: what is the probability of a passenger on the Titanic surviving, given that they were in first class? So if we look at this table here, we can actually derive information that corresponds to certain things on our Bayes theorem, right? So let's look at the marginal first, which is the probability of the evidence, right? So the evidence would be they're in first class. So what we'll do is we'll look at the first class column, which is right here. And what's the probability of someone being in first class? Well, that's just the probability, like the total people in first class divided by the total people on the boat, which makes sense. That's why we got the 325 divided by the 2,201. And the prior is the probability of someone surviving, which is just the total of the people that survived divided by the total of people on the boat. So we got 711 divided by 2,201. The likelihood, I wrote likeliness here, but it should be likelihood, should be the probability of first class given that they survived, right? So we can look at that, the probability of first class given that they survived, which you got the 203 divided by the 711. And now we can just plug and chug, into our formula and get 0.62, meaning 62% of people on the Titanic survived given they were in first class, right? So that's pretty cool. It just means that if you do the math for the other sections of people in crew, you'll find that first class tended to get the best treatment. They survived the most. It's just life, I guess. They paid for it, I guess. I don't necessarily believe in that kind of things. I think it should be life is equal to all, but that's my own personal values. Let's move on. So we know how to look at individual features. Also, we know how to do this for only like looking at if someone is or is not something, right? So how do we scale this up so we can have as many features as we desire to look at? So what I mean by is, right now we're looking at, is it a cat given that it's fluffy? But what if we have more than just, is it fluffy? Let's say it's fluffy, it has paws, it has whiskers. What's the probability, you know? And then what's the, we're just looking at a cat. Like, what happens if we're like, is it like a dog? Is it a giraffe? Is it a meerkat? Like, how do we scale this up into more categories and to more features? So we need to talk about expansion, probabilistic expansion. So if you look at here, I'm just going to go up here real quick. And I'm sorry that it's all written out. I kind of pulled this off the top of my head. So I don't have a nice picture for you guys. But I can kind of show you what I mean. There's a pattern here. So I wrote a ... d. It could be n for all that matters. It'd have the same pattern. So this equals that. I know it looks gross. It looks probably more gross than what it would be originally. And these are all equivalent to each other. They just keep expanding outwards further and further, right? So using that kind of idea of how probability expands outward, you can do the same thing with Bayes' theorem, right? So I'm looking right here, and I'm expanding it outwards. And as you can see, it gets very gross very quickly. And this is very difficult to calculate. Not tremendously, but difficult enough where we should probably make some assumptions to make us simplify a few things, right? So the first assumption we can make, right, is nothing's dependent upon each other. So when we just use straight Bayes' theorem, right, everything is still dependent upon each other, which is a good thing, right, if things are dependent on each other. But if you're looking at data that is not, that's just a lot of extra calculations that you don't need. Therefore, we can actually calculate things individualistically, where you just look at the probability of a specific piece of evidence given the hypothesis. And that's what we do. And if you look at the very bottom of the screen, you will see the probability of the hypothesis given any number of features, x1 to xn, is just the same thing as the probability of the hypothesis of any one given feature given the hypothesis, from x1 to xn, multiplied by the probability of the hypothesis divided by the probability of any given feature from x1 to xn, which is really awesome. It allows us to make a lot of things, Now, we can do even more than that. We're not done yet. We can actually see that the denominator, once we get to a certain point, is just going to converge and become a single number. And it acts more like a scalar, meaning we don't really need it. And we'll know that if we throw it out, that the probability that we're looking for is just, it's like it has a relation. It's a, there's a name for it. God. It's not an inverse relationship. It's a proportional relationship. There you go. It's a proportional relationship to the probability of the hypothesis multiplied by the probability of every single evidence given the hypothesis, right? So this is naive Bayes for binary classification. So we just handle the situation where we have as many features as we want. But how do we handle this case where we have more categories, like, cat, dog, ferret, fish? all those kinds of things. But that's pretty easy too. We're just going to take the argmax of the categories. So we're going to run this for each one of the categories we got, and whichever category has the highest probability value will basically be returned, and that's how we will determine it. Does that make sense? So like, if it's like 20% chance of being a dog, 33% chance of being a cat, and like 73% chance of being a fish, and there's a whole bunch of other ones, but the fish is the highest one, it's going to return the fish as the value. Does that make sense? Cool. But there's one big flaw with this, and that's we made too many assumptions. So what if data is actually dependent upon each other? How do we fix that kind of thought process? So there's a pretty good way to fix this, and it's just a matter of kind of looking at it in a different way and making these problems smaller, but also making it a lot more complex in a different way. So introducing something called a Bayesian belief network. A Bayesian belief network is always acyclic, meaning if you have any node A, you can't get back to node A. There is, like, for every node inside of the cycle, or not in the cycle, sorry, in the entire graph. So that means you can never get back. There's no cycles, there's no circles, you can't travel back to another node. But you can, however, travel down each node, so it's acyclic. And each one of these nodes contain a probability table that gets calculated from the nodes above it, right? So if you're a node on the very top, like a root node, you basically have a prior, and like we always had. And then if you're on the bottom, you essentially have a large probability table dependent upon everything above you. So if you look at the grass wet, you'll see there's a very large probability table there. The sprinkler has a probability table that's dependent on the rain, so its table is bigger, and the rain is a prior, so it just has two probabilities. I'm not going to go over the math on how this table was these tables were constructed at this moment. I think it's a little bit beyond what we're trying to go on for today, but I can come back to it later. So looking at this table, how do we calculate the probability of the hypothesis, which would be, is the grass wet, given the evidence, right? It's still a little unclear, right? So we need to talk about probabilities and ways you can look at these probabilities. So all of these things have a joint probability table. So is the grass wet has a joint probability table. It's looking at the rain and the sprinkler. It has a probability of, the rain being on or the sprinkler being on or off, respectively. And these joint probability tables have a combination of all these things together. The marginal probability is just a sum of the probabilities of something disregarding everything else, right? So the probability of the evidence. So what this means is, if you look at the sprinkler, right, if we don't care about whether it's raining or not, we're just seeing if the sprinkler's on or off. If the sprinkler's on, right, we get, look right here, it's going to be 7.7 and the 0.02. So being on is 0.72, and it being off would be the opposite ones, the 0.2 and the 0.08, and that's going to make the marginal probability. The conditional probability is something given something, right? So now we're looking at things when it is raining, right? These are often the things we're trying to calculate, the conditional probability table. So we're only looking at when it is raining, so we'll look at when it's raining, and we can only take these two outcomes, right? And so if the sprinkler's off, it's 0.2, and if the sprinkler's on, it's 0.02. And then we need to normalize them, because probabilities are always talked about in a scale from 0 to 1. And so I made a little bit of rounding, and it'd be basically 90% of the time the sprinkle will be off, given it's raining, and 10% of the time the sprinkle will be on, given it's raining. These are just ways to interpret data, right? This is what your computer does when implementation is happening. So how do we calculate the probability? Well, it's a combination of those three techniques, looking at any given node. So it's saying the probability of all the nodes is equivalent to the probability of every single node given its parent's node. Now, the problem with Bayesian belief networks is you need to define the network itself. And there's techniques to train the network, but they're beyond the scope of the discussion today. As well as, you need to have an intuition of how things are related together, which is not always the case. And if that's something you don't have, it might be better to use other machine learning techniques. Because, like I said, it's supervised learning, meaning the humans intervene in a certain way to define what you want to do. So now you know the math, but now what? What are we going to do? Let's talk about different versions of Bayes' algorithm, when to use naive Bayes and when not to use naive Bayes. So here are, there are many different types. So this is not an extensive list, it's just the most common types. So the classic naive Bayes is the general Bayes, right? That's essentially the most upper class, if you're going to talk about English, that's just the language, but there's so many different parts of English, right? So let's talk about specific parts or specific techniques. There's something called Bernoulli, right? Which is used for binary inputs, things that are either present or absent. And it's good for text data, discrete data, and small data sets. And what I mean for binary inputs is if it's there, it's there. If it's not there, it's not there. And if you're doing something with text data, it doesn't matter if the word bird shows up 37 times. It is there, therefore it will classify it accordingly. Gaussian, I don't think is very commonly used, but it can be used. And it assumes the data follows normal distribution. So if you do believe your data follows normal distribution, you can get a bit more mileage out of this. And it can be good for continuous data, but you need to break it and discretize it into categories of some sort. And it can also be very good with small data sets. There's something called multinomial, which is essentially Bernoulli, but it shows how much presence a feature has. So it can sometimes outperform Bernoulli in certain situations. Like if a text document only has one mention of bird, Bernoulli will probably classify that properly because it probably isn't about birds. But if the word bird shows up 37 times, 41 times, there's a good chance that that text is about birds, So this is good for text, small data sets, pictures, and continuous data. So let's move on. Where it seems to work best. Text classification, Bernoulli and multinomial. They're very good text classifiers. Computer vision, multinomial. It can be used for computer vision. It's not the best computer vision algorithm, but it can be used. And therefore, it is pretty reliable. It's pretty cool. It's very good when you have discrete features in your data. And these mean categories. It's also very good when data sets are small. So you don't need a large extensive data set to have a good naive Bayes algorithm. It is very fast. It can be trained while classifying. So one of the best and strongest things about this algorithm is that when you need to add more data points, you can just add more data points. It doesn't change the entire structure of the entire algorithm. It just changes a few counts here and there, which makes it more adaptable and more maintainable, unlike some other algorithms out there where you need to rebuild the entire model when you're trying to add another data point, where it does not seem to be optimal. If there's complex relationships between your features, this includes text classification where word order matters. The red hat and the hat is red might mean the same thing, right? But saying the pole hit the man versus the man hit the pole are two completely different things. Therefore, if you're trying to make those kinds of decisive classification, you probably don't want to use naive Bayes. There's also an issue with zero frequency, where training data does not contain anything for a specific category, meaning when it does show up, you can never classify it correctly. And lastly, if data is continuous, it might not be the best option to use naive Bayes, especially if you're trying to capture complicated relationships. If you know the continuous data is not having complex relationships, you can discretize it and it should be fine. But if it does, don't use it. And continuous data tends to have those kinds of relationships built into it. So alternative algorithms to handle some of the failures of, or not failures, but features of naive Bayes that aren't the best. Support vector machines, forests, and decision trees, they can tend to handle the situations where the data has complex relationships between them. And naive Bayes will fall short in these situations. Also, I do think that these can work very well for you depending on if you have more than certain types of data. I think if you have text data though, I would try to stick with naive Bayes or deep learning. Deep learning can learn those intricacies and semantics of text, and therefore might be able to capture things that naive Bayes cannot. Naive Bayes might capture some basic things, but it can never capture the semantics as well as you'd want them to, right? And that's pretty much it. So let's kind of go over what we learned today. We learned about Bayesian classification, which uses this theorem called Bayes' theorem, that uses a probabilistic approach to classify data. And this data is basically looked at as, given hypothesis X, what is the chances that given evidence A, B, C, and D, that it is that hypothesis, right? And then from that hypothesis, we get a classification label. And that's really awesome. And we also learned that it's really good for text classification. Hope you guys have a wonderful day. Thank you guys, and I hope you guys learned something from this lecture. I'm thinking about doing a quick Python tutorial kind of showcasing Bayesian classification and the power that it has. It's going to be a very basic tutorial. I'm not going to try to make it complicated, but I want to put it up. So, hope you guys have a wonderful day though.